Hello,
Hello.
can you hear me?
Yeah, sir.
Okay, we'll finish the theory for gravitation. So if we start off with potential derivations, have you seen the derivations for gravitational potential?
Yeah.
Are you understanding what is happening?
Yeah.
Okay, so obviously potential due to a point mass at a distance r will be V is minus G n by r.
Right.
This is the scalar potential value at this distance, and we will extend this by integration to cover different types of bodies. If there is a ring, for example, with mass m, radius r, and the point is on the axis of the ring, point P, want the potential at point P, this point is at a distance r from the ring, and the radius was, let's say the radius was given A. Instead of capital R, we'll say it is A.
Right.
So in order to find the potential, what do you do here? What is V?
Minus G dm by uh, distance of some particle. And in this case, it would be a square plus r square.
Root over A square plus
Ah,
R
sorry.
square.
Yeah, yeah. Root over.
That would be the potential due to a small mass dm at
Right.
this point.
Right.
So for the whole ring, you'll have to integrate this, and total potential, you integrate this, cover the entire ring. You have to realize that every point of the ring is at the same distance.
Right.
Because it's like this, it's a circle and the point is on the axis somewhere here. Each point on that circle is equidistant,
Right.
right?
Yeah.
So this part is a constant no matter where your dm is. So you'll get minus g by root over a square plus r square and integral dm, which will become capital M.
Right.
So that becomes your potential due to a ring at a point on the axis of the ring. Now, similarly, you could be asked, for example, what is the potential due to a disk? V due to a disk. A disk is different from a ring at a point on the axis of the disk.
Right.
So the situation is the same, but the difference is that it's not just mass on the perimeter, it's the mass is on in the area, right?
Right.
It's a disk, and on the axis of the disk at a distance r, you have the point P. You want potential, the mass is m, a is the radius of the disk.
Right.
So in this case, how would you find out the potential?
Because we had calculated for ring in the previous case, now we can use an element that is a ring itself and find the general distance for that element ring and integrate that.
So we'll say, yes, we'll say this is x, and let's say thickness is dx.
Right.
So we'll have a mass which will be like a ring mass, right?
Right.
And the distance of that point from the ring mass here is root over x squared plus r squared.
Right.
So the potential due to this ring would be V dV is equal to minus G, whatever is the mass of the ring, divided by root over x squared plus r squared, right?
Right.
According to the previous formula.
Right. Yeah.
Mass of this ring you can calculate by saying that total mass of the mass density is m by pi a square, and the area of this much is 2 pi x into dx.
Right.
2 pi x is the perimeter, dx is the thickness. So area will be the length product of the perimeter and the thickness.
Right.
So you'll get this is basically pi gets cancelled and you get 2 mx by a square dx.
Right.
So that is your mass of the ring. So now you will get basically a g minus g 2 mx by a square root over x square plus r square dx. This
Right.
is going has to be integrated in such a way that x goes from 0 to a.
Right.
So you will take minus 2gm by a square outside, and you have to do the integration of x by root over x square plus r square. X goes from 0 to a dx,
Yeah.
right?
How would you integrate this?
So integration is possible. It's you have to anyway. You will be learning about integration in maths in this year, so this is not very difficult. You just have to do a proper substitution or a change of variable. So here, if I have to integrate this, my variable of integration is clearly x, but it
Right.
would be easier to do if I change the variable and did it like this. X squared plus r square can be called t squared. T is my new variable.
Okay.
If I do this and I differentiate this, I'll get 2x dx is equal to 2t dt, right?
Right. Yeah. Yeah.
And then I will be able to say that x dx is basically t dt.
Right.
So I can replace the top part with t dt and replace the root here. It will be root over t then.
Okay. Right. Yeah.
No, not root over
Root
t. It
over
will be
t
simply
square.
t,
Yeah. T.
right? So x square plus r square. So it is, yeah, it is coming directly. It's cancelling out, right? So
Right.
integral of this will be simply t, and t was what? Root x square plus r square, right?
Right. Yeah.
I have done the integration by changing the variable. Now I have put back the old variable and I have to put the limits,
Right.
right?
Yeah.
If you put the limits, it will be root over a square plus r square minus r
Right. Yeah. Yeah.
minus, yeah, r. And finally, my potential becomes, potential is coming out to be this expression minus 2gm by a square root over a square plus r square minus r,
Right.
right?
Yeah.
So this is like a standard integration method. Again, another application is the spherical shell. So think of this spherical shell. Spherical shell means all the mass is contained on the boundary, on the surface.
Right.
It is hollow inside like a football, you can imagine. Everything is on the boundary, nothing is inside.
Right.
Did you understand the derivation that we have shown?
Yeah. I think except no, the last few steps I didn't properly understand.
Mass is m, let's say radius of the shell is a. You have to find field or potential at a point P here, which is at a distance r.
Right.
The spherical shell is like this, so we have to find a way to represent the mass contained on that shell's surface area. What we will do is use the ring concept. First, I'll draw a radius like this, which makes an angle theta like this, and I'll rotate the radius all around this line.
Right.
And then I will change the angle a little bit, and I will rotate that line also all around.
Right. Yeah.
Theta plus d theta. So this gap angle is d theta, and this boundary length will be a d theta,
Right. Yeah.
and I am rotating it all around. So I am clearly getting a ring type of situation.
Right.
This is like a ring, and the ring's points are at a distance z from here,
Right. Yeah.
right?
Yeah.
This angle is theta, this whole length is r,
Right.
and this length is z, and we have to find the potential due to the ring at this point. Now, obviously, by the ring formula, we know dv should be minus g dm by whatever is the distance of the ring from this point, which is z, right?
Right.
That's your ring formula.
Right.
And now, if you think about it, the mass of that ring, the dm in that ring would be mass density, which will be m by 4 pi a square, times the area contained in the ring boundary, right?
Right.
So if you think about it, this is a circle. The perimeter of the circle will be 2 pi into radius. Radius here is the circle. Radius is a sine theta clearly.
Yeah. Yeah.
Perimeter is 2 pi a sine theta.
Yeah.
And what is the thickness? Is a d theta.
Right. Yeah.
So circle area, the area of the ring is 2 pi a square sine theta d theta.
Right.
So this becomes m by 2 sine theta d theta. So
Right.
dv is minus gm by 2z sine theta d theta,
Right.
right?
Yeah. Yeah.
This is coming as my potential expression due to the ring, but the problem is that I cannot directly integrate because two unknowns are there. Z is also unknown, Z is also variable, theta is also variable.
Right.
As you change the position of a ring, both Z and theta will vary, right?
Right.
So I cannot integrate over two different variables. So I have to make it into a single variable if possible.
Right. Yeah.
So if you want to make it into a single variable, you will have to use some information about triangles. And let's say this is a point, this is Z, this is R, this is A, and this is theta. This is
Right.
the situation. So obviously by cosine rule, you can say cos theta is equal to a square plus r square minus z square by 2ar. So you
Yeah.
have 2ar cos theta is equal to a square plus r square minus z square.
Right.
And you are changing the positions of the rings, not the position of the point and not the radius of the circle.
Right.
So if the point is fixed and the sphere is fixed, the A and R are constant.
Right. Yeah.
What is changing is theta, z, those things,
Yeah.
right?
Yeah.
So in this expression of cosine rule, if I differentiate now, A and R are constants. So differentiation is only with respect to theta here and only with respect to z here.
Right.
So if you do that now, you will get basically minus 2ar sine theta d theta is equal to minus 2z dz,
Right. Yeah.
because this is constant. The only
Yeah.
variables are this and this.
Right.
So you get ar sine theta d theta is equal to z dz. Basically, we are getting an expression for sine theta d theta in terms of z dz.
Okay. Right. Yeah.
And that removes one problem that we had two variables here. So now we'll have one variable. We'll say dv is minus gm. Instead of sine theta d theta, I'll say z dz by ar and divided by 2z. So you get gm dz by 2ar. Right?
Right.
This becomes our expression for potential. Now the only thing that is changing is dz.
Right.
Now I have to integrate this expression in different situations to get the value of my potential. So this is the common result that we have gotten, and now we have to integrate for two cases. Case one is when the point is outside, and case two is when the point is inside the shell. P is outside the shell, and we have to integrate for potential. We have to integrate minus gm by 2ar dz, which is basically minus gm by 2ar integral dz. And you
Right.
have
Yeah.
to imagine the point being outside and see how you will vary the different rings and how does the z change, right?
Right.
So many rings can be made. How does the z value change?
Right.
If your ring was really close here and a small ring, let's say the theta tends to 0, the ring will be really small and here, and the z, if you think about it, is going to be roughly the difference between r and a, right?
Right. Yeah. Yeah.
Right now, it is not really r minus a right now because it's at an angle. But as theta tends to 0, the ring becomes a point, and the
Right.
distance is simply r minus a.
Right. Yeah.
And when you come to the other side, when theta is pi, the distance is r plus a.
Right.
So it is from r minus a to r plus a here,
Right.
and you get basically r plus a minus r minus a is going to give you 2a. So when you divide, when you divide gm by 2ar into 2a, you get minus gm by r.
Yeah, yeah,
This is for all points when p is outside the shell, potential is this.
right,
And here r is the distance of the point p from the center of the shell. And notice that it doesn't matter that there is a shell. It's almost as if it was a point mass at this point, right?
right,
So if the point P was outside the shell, it's as if the sphere behaves like a point mass at its center.
right,
While calculating potential, you can just imagine the whole spherical shell to be as if it's a point mass at the center.
right, yeah,
Then you will not have to derive the whole thing again and again. We have gotten the derivation, and from there we are making this claim that if the point is outside the shell behaves like a point mass while calculating potential.
right,
The second case is when the point is inside the shell. So again, your integral is the same, minus gm by 2ar integral dz. But now you have to think about a different situation where the point is inside somewhere here.
right,
The radius is a. The shells again have to be made. There are so many shells that could be made, right?
right,
One shell could be here. Again, what is the z? The z is the distance of the shell from the point B.
right,
So all similar shells like before, one small shell will be here and one small shell will be here when theta goes from 0 to pi.
right, yeah,
The distance of the shell from point P in this case is actually a minus r, and in this case from here to point P is actually a plus r.
right, yeah,
So the limits in this case is minus gm by 2ar, a minus r to a plus r, dz. A plus r minus a minus r gives 2r, which cancels the 2r here and becomes minus gm by a
right, yeah,
for a point inside the shell, right?
right,
So what we are getting is the potential at any point inside a spherical shell is actually independent of the distance of that point from the center of the shell.
right.
It doesn't depend on the r value, which was the distance of the point from the center of the shell. What it depends on is the value of the radius of the shell.
So it's same no matter where it is inside the sphere.
So potential inside a spherical shell is constant and it is minus gm by a.
Right,
Whereas if it were outside the spherical shell, it was variable and it was dependent on minus gm by r as if the whole shell was a single point at the center.
okay, right, yeah,
So inside and outside formulas we are getting, and that is the derivation. Now, if you have the case where it is not a shell but it is a solid sphere, so we will do the cases for this. For a solid sphere, obviously you should realize that a solid sphere can be made up of multiple shells, right?
right,
We will take a spherical shell like this. It has a radius of x, and let's say there is a thickness of dx. That's what makes it a shell.
right, yeah,
All the mass is contained in that dx portion.
right,
If the total mass is m, the total radius of the whole sphere was a. The mass density is m by, this time it's a density per unit volume. It will be 4 by 3 pi a cube. And what is the mass of my shell? It is basically the surface area times the thickness dx, right?
right, yeah,
It will be 4 pi x squared times dx. 4
right,
pi gets cancelled, you get 3m x squared dx by a cube. That becomes your mass of the shell.
right,
Now think about it, if I have a point outside, this is the distance r, and I have a shell like this here. I know how to find potential due to this small shell at the point P, right?
right,
Because I've learned in the previous case that if it's a point is outside the shell, we can sort of imagine the whole shell as if it's a point mass at the center.
right, yeah,
So potential here would be as if minus G dm, whatever is the distance of the mass of the shell, which is assumed to be at the center, to this, which is simply R.
Right.
So if you see that minus G dm is basically 3m x squared dx by a cube and R, this becomes your dv, right?
Right.
And actually we don't need to do much here because G and R are fixed now. So you can just directly integrate and say it's minus G capital M by.
Right.
The small r is fixed, G is a constant. The dm is the only thing that changes as you make many more different shells, right?
Right.
Or if you're not convinced, you can actually write it like this and say minus 3gm by a cube r integral x squared dx from 0 to a, right?
Yeah.
And so there you'll get an a cube by 3 coming, which will cancel this stuff.
Right. Yeah. Yeah.
So again, you will get the same thing.
Okay. Yeah.
So for a solid sphere, using the shell result, if the point is outside, it is obvious that the potential is coming out to be this.
Right.
And again, this is also another example where if the point is outside the sphere, we can imagine the whole sphere's mass to be concentrated at the center, and it's as if it was a situation like m mass was at a distance r from P.
Right. Yeah.
The final answer is coming as if it's also a point mass instead of a solid sphere, right? Correct?
Right.
The only other case is the
Correct. Yeah.
internal case. This is a solid sphere, and now the point is not outside, but the point is actually inside. Let's say point is here, and this distance is r. Everything is the same. The mass of the whole sphere is m, radius is a, and it is a solid sphere, so mass is distributed throughout the volume.
Right.
Now, what we will do here is we have to find potential at point P. We will do that calculation of potential in two steps. We'll break down the body into two separate spheres. One is a smaller sphere and one is the outer portion. This is portion
So why
one.
can't we say that we had found for the shell that if the point P is inside, then it would just be minus GM by A?
Is it a shell right now or is it a solid sphere?
I mean, we can again just take the shells inside the sphere.
We are going to do that only.
Oh, okay, okay,
That's the way to derive it.
okay.
I mean, using the shells only, no, we have gotten solid sphere result for outside the sphere.
Yeah, yeah.
So now I'm going to use solid sphere result instead of doing the whole shell from shell
Ah,
to solid
okay,
sphere.
okay. Right, right,
I'm going to take one solid sphere, which is a smaller solid sphere, which is basically as if it's inside and this point P is outside it.
right,
Just now in part one, we know how to do that. If it is a
yeah,
smaller solid sphere, we know how to find potential outside.
right,
So this smaller sphere is having radius of r. What is the mass in this sphere? We can say m by 4 by 3 pi a cube times 4 by 3 pi r cube.
right,
This is the mass inside the smaller sphere. Basically, it is m times r cube by a cube.
right,
And we just now saw that if the point was outside a solid sphere, it's as if the whole solid sphere was concentrated at the center.
right,
And this point is at a distance r. Potential is minus g m dash by r. And m dash is minus g m r cube by a cube by r.
right, yeah,
Do you understand what I'm getting?
yeah,
This is my m dash, which is the mass of the inside part.
right,
And my potential should be minus g m dash by r due to everything inside, which was a solid sphere.
right,
So I'm getting v, let's call it v1. V1 is coming out to be minus g m r square by a cube.
right,
Once we have this, now we have to still find out what is the potential due to all the parts which are outside it.
yeah,
In order to find that, we will think of, okay, let's split up the outside portion into shells. And let's say there is a shell right now like this, which is having radius x, right?
Right.
This shell is clearly bigger than the radius of point P. So for this shell, the potential here is fixed.
Right. Yeah.
The mass of this shell dm will be m by 4 by 3 pi a cube times the what is the area or volume contained in the shell? It will be 4 pi x square dx.
Right.
So you get basically 3m x square dx by a cube is
Right.
the mass of the shell. And potential due to this outer shell at an interior point will be minus g dm by radius of the shell, which is constant x.
Right.
So potential should come out to be minus g 3m x square dx by a cube x. This is the dv due to this shell, right?
Right.
And we have to integrate for all such shells. So we have to integrate x. All such shells will be there when the x varies from R to A.
Right. Yeah. Yeah.
You will take minus 3 gm by a cube outside, and it is x dx. So x dx integral is x squared by 2, and you'll get a square minus r squared by 2.
Right.
This is potential due to everything outside. Potential due to everything inside is this. Total potential at point P will be the sum of this plus this.
Right.
So in order to calculate that, we'll take minus gm by a cube common. You will have r square plus 3 by 2 a square minus 3 by 2 r square. So you
Right.
get 3a square by 2 minus r square by 2 and minus gm by a cube. Finally, you can write it as minus gm by a cube, 2a cube, 3a square minus r square.
Right.
This is the potential due to a solid sphere at a point inside the solid sphere, where r is the distance of that point from the center of the solid sphere.
Right.
If you put v at the center, would be when you get r is equal to 0 in this formula. If r is equal to 0, you get a minus 3 gm by 2a.
Right. Yeah.
This is the v at the center. This is the formula for potential at an internal point of a solid sphere.
Right.
All of these derivations are super important. Now, using these derivations, we can also find now similar ideas. We have to find the field. So we have found potentials. We can now find fields due to all of these types of situations. The
Right.
only difference is that in field calculation, you have to worry about the direction of the field. And it's a vector, so you have to actually do it properly,
Right.
right?
Yeah.
So let's look at some of the field parts. So first part is field due to a point mass, which is obvious. It is minus gm by r square er unit vector, where it is minus sign is because it is pointing towards the source mass, right?
Right. Yeah.
Field due to a ring at a point on its axis is super important. You have to realize that every dm creates a field like this, dE. But
Right. Yeah.
there are diametrically opposite masses, right?
Right.
Every time there is a diametrically opposite mass, in such a way it will be that the components, like for example, for this one and this one, the vertical components will get cancelled.
Yeah.
The only components that will remain is the axis components along the axis.
Yeah.
Similarly, for each of the diametrically opposite points, so if you label this as theta, you'll say that only dE cos theta matters, the dE sin theta gets cancelled.
Right.
The dE due to this dm is minus g dm by the distance square. So if this was a and this was r, it is a square plus r square. This is the dE.
Right.
Cos theta is actually r by root over a square plus r square. So it becomes a 3 by 2 and r, right?
For cos theta. Yeah, okay. Yeah.
And finally, since the point and all is fixed, when you integrate it, nothing has to be integrated. G, R and all are fixed. So it is just simply becoming G capital M R by a square plus r square to the power 3 by 2.
Right.
This is the field that is acting, which is towards the ring like this. This is the net field because we have added up all the dE cos thetas and integrated that. You get a M instead of dm. Everything else is anyway constant.
Right.
Similarly, he has derived the disk using the disk. Should be obvious what he has done. Nothing major. Take a disk as part, so small rings which are being done.
Right.
And you are going to use the formula for field due to a ring. This is the formula for field due to a ring at a point at a distance r on the axis.
Right.
You are
Yeah.
going to use this formula and try to integrate it for rings where the radius keeps varying. The a keeps varying from, instead of a, you will have an x there now, right?
Right.
And x will vary from 0 to a.
Right. Yeah.
I hope you are understanding.
Yeah.
So that is the derivation that is shown there for C part, which is field due to uniform disk at a point on its axis, right?
Right.
Now we come to the spherical shell parts. Spherical shell. Again, the whole setup is the exact same setup. You have a ring like this, right?
Right.
Point is somewhere here. The distance here is r. The radius here is a. The angles are theta and theta plus d theta, right?
Right.
This distance is z. This angle is theta, correct?
Yeah.
So literally everything is the same. The formula for field will be the ring formula that we have. Field due to this ring at a
Right.
point P.
Right.
The ring formula is dE was G dm by z squared and cos theta, right? Where theta was this angle.
Yeah. Right.
We will not write it as theta. We will say it's cos alpha. But alpha is we are calling as this angle. If you see the ring derivation, it was that angle alpha, right?
Right.
Theta right now in our case is this theta. This is theta, this is alpha. The formula should be this, right?
Right.
This is the field in this direction due to the ring.
Right. Yeah.
Now, obviously, I have to cover all such rings, so I have to integrate this, but I have a problem that there are two variables, z and alpha,
Yeah.
right? If you write the dm, the
Right.
dm comes out to be m by 2 sine theta d theta as before, right?
Yeah.
So you'll get gm by
Right.
2z square sine theta d theta cos alpha. So technically now I have three variables. I have theta also changes,
Right. Yeah.
alpha also changes, z also changes. So I have to do something
Yeah.
to remove all of these different variables and make it only one variable, right?
Right.
So just like in the previous case, he does cosine rule for this theta and he gets z square is equal to a square plus r square minus 2ar cos theta by cosine rule,
Yeah.
and differentiating it gives us 2z dz. A and r are constant, so you get a minus plus 2ar sine theta d theta.
Right.
So we get the same result as before. Z dz is AR sine theta d theta,
Right.
right? So
Yeah.
sine theta d theta is Z dz by AR. So that is one result that we had seen before also,
Yeah.
right?
Right.
However, we are still stuck with the alpha, but cos alpha is not difficult because again I've used cosine rule. I'll say cos alpha according to cosine rule will be r square plus z square minus a square by 2rz, right?
Right.
So now I can replace sine theta d theta also, and I can replace cos alpha also. I'll get
Right.
gm by 2z square. Sine theta d theta becomes z dz by ar, and cos alpha becomes z square plus r square minus a square by 2zr.
Right.
So one z gets cancelled, and this becomes 4. This is 2z ar 2 2zr. So you get 4ar square, and z square you can take inside. So
Yeah.
you will get basically the expression dE is equal to gm by 4ar square. Z square you will take inside, and it will become z square plus r square minus a square by z square, right?
Right.
And there is a dz on top because z
Yeah.
dz by ar you had done for sine theta d theta.
Yeah.
This is the expression. You can write it as 1. What he has written is 1 minus a square minus r square by z square dz, and you have gm by 4a r square, right?
Right.
This is due to a spherical shell. Point was outside here. This distance was r. This distance was z. This distance was a,
Right.
right? Now again, our expression for dE is same. We have to take two cases. One point is outside, one point is inside. So here we will take all such rings where the point is outside, right?
Right.
So obviously Z for the outside ones, Z will vary as this distance is r minus a to r plus a, right?
Right.
So the integral here is from r minus a to r plus a, gm by 4a r square, and 1 minus a square minus r square by z square, right?
Right.
So integral is z minus a square minus r square, and there is minus 1 by z. And I have to put the limits r minus a to r plus a.
Right. Yeah.
So you're getting z plus a square minus r square by z, right?
Right.
And evaluated from r minus a to r plus a. So when you put r plus a, you get what? R plus a, and this becomes plus a square minus r square by r plus a. So that will be a minus r
Right.
minus r minus a minus a square minus r square by r minus a.
Not
So that
right.
would be negative of a plus r, right?
Right. Yeah. Yeah. Yeah.
R gets cancelled. Here you are getting plus a plus r, and this r gets cancelled with this. This plus a, so plus 2a and plus 2a, so plus 4a, right?
Yeah.
Finally, plus 4a comes, which gets cancelled like this, and the field comes out to be gm by r square.
Okay. Right.
So the overall field is coming in this direction, and its magnitude is gm by r square, and it is actually as if the whole solid shell, spherical shell, was concentrated at the point here, right?
Right.
So if the point is outside a shell, you can always think of it as concentrated at the center of the shell.
Right.
right?
Yeah.
If you do the same case here for a point inside the shell, you have to only change the limits of integration. This distance is a minus r minus a. No, no. This distance is a minus r to this distance is
AMI.
a plus r.
Yeah.
Now the limit is from a minus r to a plus r, right?
Right. Yeah.
Everything is just same, a minus r to a plus r. And when you do that, first two terms are same,
Yeah.
right? First two terms are same. The only thing that changes here is when you do minus, you have to do minus a minus r. It is basically plus r minus a, right?
Right.
And you have to do minus a square minus r squared by a minus r. So minus a minus r, right?
Right.
And now you will see that from here you're getting 2a, and from here r minus a minus r, you're getting minus 2. It
Right.
is
Yeah.
2a minus 2a is becoming 0.
Right.
So what we are getting from the same derivation is that E is 0 inside a spherical shell at any
Okay.
point. It is irrespective of where the point is located inside the shell. And E is gm by r square, obviously pointing towards the shell,
Right.
right? If the point is outside the shell at a distance r from the center,
Right.
right?
Yeah.
Once you get these two spherical shell results, we can define our solid sphere results also on the basis of these. Because our
Right.
solid sphere can be built up of many shells.
Right. Yeah.
So if the point is outside, it is super easy. Take a shell of x and dx, and due to this shell, the field here would be simply g dm by r squared, right?
Yeah.
So all the shells, it is an external point, so it is always going to follow this formula, the
Yeah.
second one.
Yeah.
So you have to just integrate g dm by r squared to cover all the shells, right? If the point is outside, for every shell you are getting this, right?
Right.
So the integration is simply this, so it will be g capital M by r square, right?
Right.
So even for a solid sphere, E is equal to g capital M by r square for a solid sphere for a point outside the shell. P is outside. P is outside the sphere.
Right. Yeah.
However, for a point inside, you have to be a little careful. Let's say the point was somewhere here, right?
Right.
We have to find the field at this point. Obviously, we know that due to a shell, field is there outside the shell, but field is not there inside the shell, right?
Yeah. Yeah.
So any shell which is outside the point P cannot do any field, right?
Yeah. Right. Right.
So all of the portion outside can be deleted. You can almost imagine that they don't contribute to field.
Right. Okay. Yeah.
So the field is only going to be to the point inside the sphere, right?
Right.
And we know what happens if you have a sphere and a point is outside the sphere. It's almost as if the whole sphere's mass is concentrated at the center, and this is the g m dash by r squared, right?
Right.
And if you think of what is the m dash that is contained inside, it is easy. It is m dash is m times r cube by a cube.
Right.
So it will be g m times r cube by a cube by r squared.
Right. Yeah.
So field inside a solid sphere is g m small r by a cube.
Right.
And what we are getting is that clearly the field inside is being linearly increasing with r. And as you see, r tends to a, when you're coming at the exterior boundary, it becomes gm by a square.
Right. Yeah.
And as you go away, it becomes gm by r square and all. Now it becomes 1 by r square proportionality.
Right.
Field graph will be like this and then like this. This is when it is field is linear, when it is inside here r is equal to a.
Right.
So that becomes your field calculation inside and outside the sphere. Now after this point, what we have is basically some special cases. For example, Earth. If you have the Earth and you have to think about the gravitational attraction G value due to the Earth. So you have to first of all realize that this G value is like the gravitational field due to Earth.
Right.
Why? Because the way we have used G so far, we say force on a mass is mg, right?
Right.
So actually force was equal to G small m capital M by R square, right?
Right.
If we are writing it as mg, we are sort of saying that it is m times some E, right? So
Yeah.
E should take the place of the G, right?
Right.
Technically, your G is the field due to the Earth,
Right.
right?
Yeah.
Gravitational field due to the Earth, which is G capital M by R square,
Right.
where R is the radius of the Earth here.
Right.
Because the mass, if it was near the surface of the Earth, this is the R capital R. So the question is, how does acceleration due to gravity vary as you go up or down? If you go up by a distance h, where h is much much smaller compared to radius of the Earth, what you will get is gravitational field is gm by r plus h whole square, right?
Right.
Because the point is outside the solid sphere, that is Earth, and the distance is r plus h.
Right.
So from the previous derivation also we know this is what is supposed to happen.
Right. Yeah.
Can take r square common and it is 1 plus h by r whole square. We can write it as gm by r square 1 plus h by r power minus 2. And
Yeah.
this part is your small g, which is small g 1 plus h by r power minus 2. And binomial theorem expansion you might have learned in 11th
Yeah.
grade.
Yeah.
So you can expand this and write it as 1 plus nx plus more terms. So you can
Yeah.
say 1 minus 2h by r plus, technically there will be more terms, but
H
the
is
terms will
small.
be h
Yeah.
square by r square type of terms.
Right. Right.
So you will ignore those terms and you will say g into 1 minus 2h by r is roughly the field or acceleration due to gravity as you go up.
Right.
This formula is obviously only valid for this approximation.
Right.
If you have h is r by 3 or something, then you cannot really use this approximation. You have to directly find h is r by 3 and directly find from here,
Right.
right?
Yeah.
On the other hand, if the particle is coming down into the earth by a distance d, this was the radius of the earth capital R. Now what is the field here? Now this is the case of inside a solid sphere, right?
Right.
Field inside a solid sphere is given by gm small r by a cube, according to the
Right.
formula that we have derived.
Yeah.
So in this case, it will be gm small r is this distance actually, which is capital R minus d by capital R cube, right?
Right.
So again, you will get gm by capital R square, r taken common 1 minus d by r, right?
Right.
Which is basically small g 1 minus d by r.
Right. Yeah.
So field as you go inside the earth, the gravitational attraction changes, but it changes at a different rate, 1 minus d by r. As you go above, it changes at 1 minus 2h by r.
Right.
Slightly different variation. What you have to realize is this is an exact value. There is no approximation here.
Right.
We have never used any approximation. It's direct calculation of field.
Right. Yeah.
This was an approximation because we were doing 1 plus h by r power minus 2 and all.
Yeah.
So this is an approximate thing. This is an exact thing.
Right. Yeah.
That is your variation of g due to the solid sphere concepts. And then we have planets and satellites and escape velocity and stuff and exercises. So planets and satellites, escape velocity, and Kepler's laws. These three topics we'll do in the next class.
Uh,
Uh,
uh, yeah. So one thing before the end, I think in the like few weeks ago in the maths class, you had uh you had taught how to find the period of like two trigonometric functions, right? Like if we had cos 3x plus sin 2x like that. What about if they're multiplied together? Like if it was cos 3x into sin 2x, how would we do it
And
then?
express it as a product sum. If you have like this, you will just do half half and write it as a sum and difference of sin c plus sin d and all.
Okay. Oh, okay, okay.
You can easily
Ah,
write it as sine of c plus d by 2 and all. No, sine
right,
of 5x plus sine of minus x.
right, yeah. Okay, okay,
Sine 5x minus sin x should be this.
right,
Now I will write period of this is 2 pi by 5. Period of this is 2 pi. So LCM period is 2 pi.
right, okay. Yeah,
Right?
yeah, that's it.
Go through the gravitation exercises, examples, and all. Make sure that you are doing that. We'll finish the thing in the next class, but you have to try the questions and see if you're understanding how to apply the things that you have done.
All right.
So we can do the next class on Monday if you're free by if you have done it by then.
Okay, yeah,
Fine, that's all for now.
all right. Thank you, sir. Bye.